Chapter 5, problem 25.
Three rescuers are pulling horizontally on a safety net to keep it taut. One pulls northward with a force of 270 newtons. The second pulls on a direction 30 degrees south of west with a force of 240 newtons. In which direction and with what force must the third pull to keep the net stationary?
Okay, so I've got this safety net. I have 3 people pulling on it. I have 1 person pulling north with some force. We'll call it F1. Pulling north, force F1. I have another person pulling with a force, 30 degrees?
South of west.
South of west. Where is south of west? Which is this quadrant south of west? This quadrant? No, this quadrant? Yes. So this would be west. South of west would be 30 degrees south of that. So we do 30 degrees south of west. Okay. All right. And the final, so that we'll call that F2. And then the final thing that we're asked about is what is the direction and the magnitude of the force that the third person needs to pull to keep this thing taut. So which quadrant do I need to be in? 1, 2, 3, or 4? 1, 2, 3, and 4. I need to pull in 4. With some force F3 at some angle. I don't know what that angle is yet. Okay, so I have things acting at angles. What have I said about any time you have things acting at angles? What do? Break it down. Start breakdancing? No, I'm not going to break it down. So we start breaking it up into x and y components, right? So let's break this up into x and y components. We'll do all x components in, we'll do dark blue. So I'm going to have some little bit in the x direction, and I'll call that F2x. Some little bit in the x direction for F3, we'll call that F3x. So I'm just breaking these up into x and y components. Okay, so that's the x. Now I need to break up into the y. I have F2 going a little bit in the y direction. And I have F3 going a little bit in the y direction. How about F1? Where's its x component? Doesn't have one. It's going entirely in the y direction. Okay. So now when I want to actually solve this, I need to take this picture, keep it in mind, and I need to write things out in the x and y directions. So there's something new that this iPad lets me do. I'm experimenting with it, so we're going to try. Yeah, this might fail miserably. Let's see. I'm supposed to be able to shrink pictures and move them. Yeah. So we can keep that picture in mind. We can keep watching it, and then we can actually write out things going on in each different direction. So we can write out what's going on in the x direction, and we can write out what's going on in the y direction. And I want to sum up all the forces that are going on in each direction. The sum of the forces in the x direction has to be equal to the mass times the net acceleration in the x direction. How fast is this taut thing that they're throwing people onto? How fast is it moving in the x direction? Is it moving at all? So what's the acceleration in the x? 0. So the net force in the x direction has to be 0. What are the forces in the x direction? Let's plug those in. F sub x. Let's say anything that's moving to the right is positive. Anything that's moving up is positive. Anything moving in the opposite directions would then be negative. So which forces in the x direction are positive? F3x is positive. We can see that in our picture, F3x is moving to the right. Any other forces moving to the right? No? Any forces moving to the left? What's moving to the left? Okay, minus F2x. What is that equal to? 0. So we know F3x has to be equal to F2x. Yeah? When I'm writing these out, do I want to just leave them as F2x and F3x? What have we always been doing with these?
Just change the mass and acceleration. F equals ma, just replace these two.
Semi. Were we given a mass and an acceleration? What were we given? We were given a force. What forces were we given? Were we given F1? Did they tell us a number for F1? What is it? 270. Did they give us a F2? Yeah? What did they give us? 240? Did they give us F3? No, that's what we're looking for. So I have F. What else do I have? What else did they give us? They gave us an angle. They gave us theta 2 is equal to 30. So can I write F2x in terms of F2 and theta? I can. How can I do that? What part of the triangle is that? F2x is right next to the angle, so F2x is going to be the adjacent side. What trig function is the adjacent side? Cosine. So that means F3x is going to have to be equal to F2 times the cosine of theta. We did this all last chapter. We're going to keep doing this nonstop, breaking things up into components. So I now know what F3x is. I'm looking for F3 though, right? So how do I get an F3 in there? How do I write F3x in terms of F3? Lots of mumbling.
F3x is
F3
cos of theta
cosine
divided by
theta 3 equals F2 times cosine of theta. Yeah? So I'm looking for F3. I'm looking for theta 3. I'm looking for two variables. Do I know what F2 is? Yeah, what's F2? 240? So why don't I plug in some numbers, because you like plugging in numbers, I'm sure. F3 times cosine theta 3 equals 240 times cosine of 30 degrees. Okay, so I have two unknowns in this equation. Two unknowns and one equation. What do I need to do to find the other unknown? I need one more equation. So I can look at what's going on in the y direction. What is going on in the y direction? Sum of forces in the y direction. I'm going to go straight and jump to say that that's equal to 0. Why is that equal to 0? Because it's stationary. Nothing's moving in the y. What forces are acting up? F1 is going upwards. And we can see that in our picture. That's the only force that's going up.
minus F2y
Minus F2y
and minus F.
minus F3y. Okay. Can I plug in some numbers? Can I plug in F1? What's F1? 270 newtons. F2y. Can I plug in anything for that?
Yeah.
240. Wow, that's some horrible handwriting. 270 minus 240 times what? Sine of 30 minus f3y would be f3 times sine of theta equal to 0.
Isn't theta 3?
Hmm?
Isn't theta 3?
Yeah, theta 3. Okay, how many equations do I have? I have one equation here. I have another equation here. How many unknowns do I have? 2 unknowns. Can I solve those? In theory, yes, I can.
Well,
These things. We know that f3 times cosine of theta 3 has to be equal to f2 times cosine of theta. f3 cosine of theta 3. What was f2? It's 240. Cosine of the angle, what's the angle? 30. f3 times cosine of theta is equal to, let's plug that into your calculator. What number do you get for f3 cosine of theta? Yes? 208 newtons. We like numbers, right? f3 cosine theta equals 208. Yeah? All right. We have an equation in the y direction too, don't we? We have f3y equals f1 minus f2 times sine of theta. We just got that. What was f1? 270. Minus f2 is 240 times sine of 30. f3y. If you plug in everything and solve for f3y, what do you get? $150 newtons? Good, that's what I got too. Yeah? Yes?
When you wrote out the other term, wasn't the F2 sine theta minus F1?
It would be f2 sine theta minus f1 equals negative f3y,
Because it would be
if we go all the way back to here.
F1 minus F2y minus F3y. So it's negative.
What do I know now in this picture? Do I know what f3x is? What is f3x? 208. Do I know f3y?
Yeah.
Yeah, what is that? f3y is what? Negative 150, because it's going down. Yeah? They're both in newtons. So these are making a triangle, aren't they? I have an f3x and f3y. 208, 150, and they're going to give me a magnitude of f3 and some angle. Can I find f3 from the numbers that I'm given? How can I find f3? Pythagorean theorem. So f3 is what? Square root
of f3x squared
of 208 squared
plus 150 squared.
plus 150 squared. Plug those numbers into your calculator. What do you get? 256. How do I find theta? Inverse tangent. Or sine, or cosine, any one that you want. If I use tangent, what am I doing? What's the opposite side? 150. What's the adjacent side? 208. 150 over 208. Theta is the inverse tangent of 150 over 208. And what angle do you get? 36 degrees. That is the entire problem worked out in insanely gory detail. Chapter 5, number 39. So in here, we're giving two chandeliers, right? We're given masses of each of those chandeliers. So let's write down everything that we know. We know the mass of this first chandelier is 10 kilograms. Bless you. We know the mass of the second chandelier is 3 kilograms. And we know that they're both hanging here. My chandeliers are ugly. They're boxes. That is the situation we have. First thing we have to do is draw a free body diagram. What does that mean? What is a free body diagram? Draw all the forces acting on it. What forces are acting on these boxes? Tension and gravity. Where does gravity go? Down. So I have gravity. Let's look at the bottom box first. I have gravity acting down on this box, don't I? So I'm going to identify gravity going down. With some force of gravity 2. Force of gravity on the second box. Yeah? Now, if there were no other forces acting on that box, what would happen to it? It would be falling down. Is it falling down? No. What force is keeping it from falling down? The tension. So where does the tension act? Up. We have tension in this cord. I'm going to call it T2. Any other forces acting on this second box? Normal force?
Or that's just on contact.
Normal force only acts when you have contact. Do we have contact of these things on a table or anything? So are there normal forces? Nope. Anything else? Nobody's swinging from it yet. The song hasn't started, so that they can't swing from the chandelier. First box. What are the forces acting on the first box? Gravity. Where does gravity go? Gravity goes down. So we'll call that force of gravity on the first box. What other forces are acting on the first box? The second box. And how much force is that applying? And how is that applying the force? Where is that force actually coming from? Where are you feeling that force? Maybe it's a bad way to phrase the question. It's the tension in the rope is pulling it down. Yeah. So we have T2 also acting down on the first box. So tension 2 is acting up on the second box, but is acting down on the first box. Same tension, just acting different directions on the two different boxes. Yeah? Okay, right now it looks like we have two forces pulling down on that first chandelier. What direction would that chandelier be going? Down. This would make a good movie, good action movie. How do we keep the chandeliers from falling? We have another cable. What should we call that? T1. Whoa, brilliant. Ingenious. T1 acting up. Yeah? Any of this seem confusing so far? This is all pretty good? Okay. Let me erase. No! My eraser's not working. Maybe I can shrink. Shrink and move. You don't understand how awesome that feature is. None of my previous lectures I could do that feature, and this is great. Okay, so what should I do now? I did the free body diagram. That's part A. I just got a perfect score on part A. Hey. Now we have to do what?
You have to find the tension in each.
Find the tension in each chord. So I need to find T1 and T2. So I need to write down the sum of forces acting on each one of these chandeliers. Which chandelier should you start with? Why the bottom one? You have to add the bottom one to the top one, right? There's less forces acting on the bottom one, so start with the easier one. So let's look at box 2. What forces are acting? Let's write down our Newton's second law. Sum of forces acting on this box. I'm going to throw in a trick question. What is the sum of forces acting on the box in the x direction? 0? Why is it 0? It's not swinging back and forth. It's 0. We don't need to worry about it. I'm just going to erase it. We need the sum of forces in the y direction acting on this box.
0.
Yeah, 0?
Yeah, because no.
Yeah, because it's not moving. Okay. How does that help us? Does that help us at all?
Yeah.
It does. What else do we need to do, though? We need to actually identify the forces in the y direction, right? Let's explicitly write them out. What forces are acting to pull that second chandelier up? T2 is acting up on the second box. What forces are pulling it down? FG2 has to be equal to 0. So tension 2 has to be equal to FG2. Tension 2 has to be equal to FG2. What is FG2? Mass 2 times gravity. Do I know what mass 2 is? Yes. Do I know what G is? Yes. Can I find what T2 is? Yes. Let's actually plug in our numbers and find what T2 is. T2 has to be equal to M2, which is 3 kilograms, times G. What is G? 9.8 meters per second squared. Why didn't I plug in a negative? Well, first question, what is 3 times 9.8? 29.4. We just did that in our head. Okay, so I now know what the second tension is. But why didn't I say that G is negative? Why didn't I plug in a negative number there? Hmm? So it's a positive force, okay.
Can you have a negative?
I thought G was always negative, though. Why isn't it negative here?
Can you have a negative?
Because you added it to the other side, it was negative.
Yeah, but here, the tension 2 is pulling it up. Yeah? FG2 is pulling it down.
But you moved it to the other side.
So why do I not plug in a negative here? Let's look at what I actually did, right? So I already accounted for the negative when I wrote this out. I accounted for the direction of everything acting. Yeah, in the acceleration equations, when you're plugging those in, usually you haven't accounted for the direction explicitly in writing out those equations. Yeah, so you need to plug in a negative. So in the 1D equations of motion, you're usually plugging in a negative G. In the force equations, when you are using G in force problems, you account for the direction when you're writing out this sum of forces. So plug in a positive G. Okay? Okay. Now let's do box 1. What are the forces acting on box 1? What forces are pulling it up? Well, let's start at the beginning. Sum of forces on box 1. What is it? Is box 1 moving? 0. What force is pulling it up? T1. Any other forces pulling up? No. What forces are pulling it down? FG1. And what else? And T2. Anything else? Isn't FG2 pulling it down?
No, it's the same with T2.
FG2 is pulling it down in the form of T2. Okay? So T2 is the force of the second box. So T1, which I'm looking for, is equal to FG1 plus T2. T1 equals FG1. What is FG1? What is FG? MG. Dear God, we should all know that that's MG. I don't want to stand up here and chant that anymore. M1 times G plus T2. T1 is equal to M1, which is 10 kilograms, times G, which is positive or negative? Positive 9.8. Why? Because this is a force equation. We accounted for direction already right up here. And then plus T2. What's T2? 29.4. Plug in these numbers. And what do you get? You got what? Say that again. I just didn't hear. 127. Okay. Chapter 5, number 71. We have the world's most demented stick figure woman with the longest arms imaginable and a very bad haircut pushing a box up an incline. Yeah? Yes?
How is she pushing a box that on a slope that doesn't have any friction on it?
She's wearing fancy shoes that provide friction. Her feet have friction. I don't know how she's doing it. She's magic. Here. She's a wizard. Or I guess it'd be a witch. Okay, so we have a witch that is pushing this box up by flying on her broomstick.
No, that's a flaw.
Okay. So that's a good question. That is a very good question. So we have a witch pushing the box up, apparently. And she's pushing horizontally on this box. The first question we are asked to do is to draw a free body diagram of all the forces acting on this box. What are the forces acting on the box? You already said gravity. Where does gravity go? Straight down? Straight down. What's the letter for gravity? FG. And what is FG? It's frickin' MG. FG is MG. Did they give us a mass for this box?
Yep.
Yeah? So what's the mass of the box? 60 kilograms. And we all love plugging numbers in as quickly as we possibly can. So go ahead and plug your numbers in. Find what FG is. What is FG? Roughly 600. What is it? 588. Okay. Did we have to find that number right now for part A? No. What did part A ask us to do? Just the free body diagram. Are we done with our free body diagram? What other forces are acting? The what force? Normal force. Every year, about half the physics class calls it the natural force. I don't know why. I don't think I say natural force in the lecture at all. I should rewatch it. Yeah. Puppies and kittens.
People laughing.
People laughing. My wife. Yeah. I'm doing physics, how could it not be fun? Where does so there's a normal force acting, where does the normal force act? Yeah? Is that a question? Perpendicular to the incline. It's an answer. So what is perpendicular to the incline? How do I draw that? This way, okay, yeah, yeah. So we have this normal force, Fn. I call it the Fn force. Okay. Anything else for our free body diagram? Yeah, now you're all going to call it natural force. Yeah. Gives me points that I can take off. The challenging part of these kinds of problems is figuring out the coordinate system to use. Right? Normally, you write out your coordinate system and you just have x and y. Yeah? If I do that, if I use x and y, then I end up with things acting at angles. I don't want that. So usually what you want to do in these problems, and I'll suggest it in this problem, is you take this coordinate system and you rotate it. Actually, I can maybe show you that. So this is your normal coordinate system, x and y direction. You take this coordinate system, up, don't want to do that, and you spin it around. So you take this coordinate system and you rotate it 45 degrees. Yeah. So instead of your coordinate system going up and down, the coordinate system goes up and down the incline. So what you want is a coordinate system that acts like this.
Wouldn't it be 30 degrees and not 45 then?
So yeah, I guess you rotated 30 degrees. So let's rotate that, use that as our coordinate system, a rotated coordinate system. And let's break out our pieces into their components along this new coordinate system. Which of these forces do I need to break up into components if my coordinate system is this rotated one? Do I need to do anything to the Fn force? Nope, because it's acting entirely in the y direction. It has no components. What about the push force? That is now acting at an angle. I need to break it into the x and y components. So I have one piece that's going to go along the incline. We'll call that FPX. And I have one piece that's going to act downwards. What shape did I just draw? Triangle. I probably need an angle in this triangle. Do I know any of the angles in this triangle? That's going to be 30 degrees. Yeah. Okay? All right. Let's look at FG, force of gravity. Do I need to separate this into components? Well, this is at an angle with respect to my new coordinate system too, so I need to break it up into components. I need to have one that's perpendicular to the incline. Make that FGY, and one that's parallel to the incline. That's FGX. Do I know any of these angles in this new triangle? Right, I have this triangle for gravity. Can I figure out any of these angles? Yes, Albert.
The one at the top?
The one at the top. This one?
Yes.
Okay.
It's 30 because the opposite on that one has to be 60 because the other one was in there.
Okay, so let's see if I can follow this. Whew. So you're saying this angle right here is 30, yeah? So then this angle you're saying has to be 60?
Yes, because those.
Because this is a right angle.
Yeah.
Yeah? Okay, so then if this angle is 60 And then this angle here is a right angle. 60 plus 30 gives me my new right angle, gives me my triangle. Welcome back to geometry. Okay. Now, using all of this information, I can actually completely solve this problem. And we will do that next time.